7.2 Areas in a plane. Ladies and gentlemen, today we are going to revisit the idea that an integral is an area. But whereas before we looked at areas between just underneath a curve, between a curve and the x-axis, today we're going to restrict it to areas between two curves. Look at what happens when the curves intersect various times, throw in some boundaries, and talk about when it's appropriate to integrate with respect to y, and then maybe even use some geometric formulas to save time. Area between curves. Let me move the screen here a little bit so you can see the whole picture. The idea of finding area between two curves goes back to what we did when it was just area under a curve, when we were finding the areas of rectangles, as you see here in the illustration. The area is found by finding this distance here from top to bottom and then multiplying it by the height. It's just base times height, the regular area of a rectangle. And then we take that rectangle along with all the ones like it and we add them all up. That's the sigma notation, and that gives us the answer. And of course, as we have mentioned in earlier classes, the only way we get the exact answer in all of this is by using infinitely many rectangles that are infinitely small. And that brings us down to our formula down here. To find the height of the said rectangle, we will take the upper function, its value, and subtract the lower function, and that gives us the distance between the two. And this here is our formula for finding the area between two curves. Alright, skip the last slide, it wasn't overly important. So now let's go straight to an example. We're going to find the area between y equals secant squared x and y equals sine x from 0 to pi over 4. Now a couple things we'll mention about this. First of all, as I move the screen down just a little bit so you can see everything, I am telling you on this one that it is from 0 to pi over 4. Sometimes those limits of integration are given, sometimes it's not. And we'll work out somewhere it's not so that you get that practice. I always encourage people to make sketches of this because it is important to know which function is on top, which one is on the bottom. If you flip-flop the two in your problem, you're going to get a sign error in the answer. So we see that secant squared x graph is up here. Sine is down here. This is something you can graph on your calculator. And so we know that secant squared is the larger function. Notice that they don't cross each other at all. Secant squared is always on top, sine is always on the bottom. So we set up our integral. Integral from 0 to pi over 4, that was given in the problem. The upper function secant squared x minus the lower function sine x. The antiderivative of secant squared is tangent. The antiderivative of negative sine is positive cosine from 0 to pi over 4. Plug in your numbers and subtract. That gives me 1 plus radical 2 over 2 minus 0 plus 1, which all simplifies down to be radical 2 over 2. And move the screen back up here. Alright, find the area of the region enclosed by the parabola 2 minus x squared. That's what we have here. And the line y equals negative x. Now notice that on this one I do not give you your limits of integration. You don't have a starting point and a stopping point. So the first thing we need to do is we need to find out what those numbers are. So now, where are these two functions equal? Where do they cross? So I simply set the two functions equal to each other. 2 minus x squared equals negative x. Simplify, moving things to the left-hand side, making x squared positive. And we factor and we solve. And this is verified by the graph. You see that they first of all cross at x equals negative 1. And they cross again down at x equals positive 2. Now our integral will be the integral from negative 1 to 2 of the upper function, which is the parabola, minus the lower function, which is the line. Here we go. Simplify it a little bit maybe. And then we solve. You can use a calculator to solve. You can solve by hand. I'm solving by hand. 2x minus x cubed over 3 plus x squared over 2. Plug in your 2, plug in your negative 1 and subtract. And you do get 9 halves. Alright, now sometimes working things out by hand is not a possibility, and on the calculator portion of the AP exam I've seen several of these kinds of problems. We're going to look for the area of the region enclosed by x squared minus 1, which is this bottom graph, and 2 cosine x. So we use our calculators to find where these two things cross. Whereas if you do set them equal to each other, 2 cosine x equals x squared minus 1, you really have no way outside of Newton's method to solve for x. And quite frankly, that's impractical. Newton's method takes time, and time is one of the things on the AP exam that you really don't have a whole lot of. So I graphed this on my I graphed these two individually on my calculator. and I tell it to do the intersect, find where these two things cross. And when you do that, you find that they cross at positive and negative 1.2654 roughly. If you're ever wondering how far to go decimal wise, 3 or 4 decimal places is always good. So now we set up our integral from the lower intersection to the upper right here. Remember, the cosine graph was on top, the x squared graph was on the bottom, so we subtract. And again, there's no real way to work this out by hand because of these numbers here. I mean, you could know the antiderivative. Sorry about that, ladies and gentlemen. The phone rang. As you know, I'm a very, very important, busy man. But here we go. Back to the problem. Again, you could find the antiderivative of cosine and x squared minus 1, but quite frankly, would you want to and then have to plug in these numbers by hand? So just use your calculator, and you see it's about 4.9949, probably even closer to 5 by the time we take away the rounding error. All right, example 4, finding area using subregions. Now, if we find the area between y equals radical x and y equals x minus 2, a funny thing happens. I got the graph drawn for you here. You see that actually we would break it up into 2 completely different subregions. Remember when we were finding the height of the box and you did the upper function minus the lower? Well, if we look at region A, for instance, the upper function would be this curve here, radical x, but the lower function would be the x-axis. Let me move the screen down so you can, there you go, there you can see it a little better now. But then when we go to region B here, you again see that the upper region, or the upper curve, is radical x, but the bottom is no longer the x-axis, it's the line x minus 2. So in this situation, we do need to break this up into 2 separate integrals. First of all, we'll do region A from 0 to 2, which we can find from the graph. And again, upper is radical x, the lower is the x-axis, which is 0. So if you wanted to put radical x minus 0 so that it looked like this one, you could, but of course minus 0 does nothing. And then we have the region B, which is from 2 to 4, upper function minus lower, radical x minus 2. Solve these by hand or work them out however you want to do it. I'm solving them by hand. I took the antiderivatives, plug in your numbers, and we get this long mess here. Simplify a little bit, subtract, combine things together, and in the end we end up with 10/3. Not the prettiest problem in the world, but certainly doable. If a few steps back you had just plugged it into your calculator, you would have gotten 10/3, and you could have skipped all these steps of plugging things in. Now, what about this idea of integrating with respect to y? Just like on the last problem, sometimes instead of using boxes that run up and down, it's easier, as it would have been on the last problem, to use boxes that run left and right. Now there's the problem here. On the first ones, our functions, when we were doing the width of the rectangles, the width was denoted by delta x, a change of x. These rectangles do not have a width of delta x, they have a width of delta y. Now, all that means is that all of my functions, if I do it this way, all my functions are going to have to be in terms of y and not x, as we see down here. And again, we're talking about height distance differences on this one, not necessarily horizontal. So we go C to D instead of A to B. Alright, let's go back and let's rework that last problem. This time, integrating with respect to y instead of x. Now, when we're doing it this way, we're not looking at up and down on the box, we're looking left to right. And then if you look, the leftmost function is always radical x. The rightmost function is always the x minus 2. But again, since I'm going to integrate with respect to y, I need to take each of those functions and solve for x in terms of y. So if we take this, we square both sides, y equals radical x becomes x equals y squared. Y equals x minus 2 here, if you move some stuff over, becomes x equals y plus 2. And now what is our height that we're going, instead of going from 0 to 2, we're going actually from 0 to here. So I'm sorry, 0 to 4 on the first, but now we're going 0 to 2 on the height. As you see, here is the 0, and then there's the 2 of intersection. Were we going the other way, it would have been 0 to 4. This way, it's going 0 to 2, use the y values. And so we take the rightmost function, which is y plus 2, subtract the leftmost function, which is y squared. That gives us y squared over 2 plus 2y minus y cubed over 3 antiderivative. Plug in your 2. Of course, we don't have to plug in the 0. It does nothing. And then simplify. And you again end up with 10/3, which is good. We should have gotten the same answer. Alright. Example 6, making the choice. Find the area of the region enclosed by the graph y equals x cubed and x equals y squared minus 2. So our job is to figure out which function are we going to use. Now, if we use a function that uses vertical rectangles in terms of x, you see that right here we're going to have to deal with one situation, because once we hit this point right here, the bottom function changes. And then here we would have to do another situation. If we go left to right, it looks like this is always the right function, this is always the left function. If we take our function y equals x cubed and we solve, we get x equals y to the 1/3. X equals y squared minus 2. If you were to solve that, though, you would end up with a radical. We don't want to do that, though. We want to. Let me back up just 1 second and explain why we don't want to do that. If you were to solve this one for y, ladies and gentlemen, because you see this one was y in terms of x, this was x in terms of y. The reason I don't want to solve backwards is because of the plus or minus situation, and that certainly creates more problems. So to keep it as simple as possible, I will solve this one for x, and as this one was already solved, I'll leave it alone. And now we'll take our integral. So we had the integral from -1 to 1.7930. Where did I get those numbers? Well, again, you can take these two functions, although really you'll want to take this function here and this function if you solve it for y. Again, doing a plus or minus case, and graph them, and then use your calculator to find the points of intersection. And you find that these are the 2 points. Here's the -1 right here. Up here is the 1.7930 right here where it intersects. And now we can again work this out by hand, or because of the number, just punch it into the calculator, and it's 4.2149. That's the area between those two curves. Alright. Using geometry, we're going to go back to this same example that we've worked now a couple times, and this time we're going to use the geometry formula to find the answer. It wants us on this one to subtract the area of a triangle from the radical, the square root curve, and then come up with the answer that way. So to do that, now we're just looking at the regular area underneath the curve from 0 to 4 of radical x. That would give us all of this, blue and purple area included. And then I take away from that the area of a triangle. Well, we all remember area of a triangle is 1/2 base times height. The base goes from 2 to 4, so that's 2. The height goes from 0 to 2, that's 2. Antiderivative of radical x is 2/3 x to the 3/2. So from 0 to 4. 1/2 of 2 times 2 is just 2. Plug in your 4. The 0 does nothing. 4 to the 3/2 is 8. 8 times 2/3 is 16/3. And then 16/3 minus 2 gives me that same answer of 10/3 several times. So you see you have several options when it comes to finding the area underneath the curve. And that is it, ladies and gentlemen. As always, bring all of your questions to class tomorrow, and we will sit down and discuss them.